Hello students, and welcome to our lesson on two-step equations. Now before I even get into it, I want to be honest with you that title is a little bit misleading. The ones you see on your screen right now, which are the first 6 problems, those are truly two-step equations. Everything after that is actually going to have more than 2 steps. But once we cover how to do two-step equations, then the extra steps are just other things we've already learned in this course. So the real new thing is the two-step part. So let's go ahead and dive into this. A two-step equation is going to differ from a one-step because instead of just doing one inverse operation, a two-step equation is going to require two inverse operations in order to get that variable isolated. As a general strategy, and we are going to see some contradictions to this, but this is a general strategy, you want to use the additive inverse first, where if you recall, the additive inverse is how you move, quote unquote, move terms from one side to the other. And we're going to use that additive inverse to get the variable term alone. So we're going to put everything without the variable on one side and everything with the variable on the other side. Then we're going to use the multiplicative inverse. Oops, if I could spell, multiplicative. And the multiplicative inverse is going to be what makes our coefficient 1. So in one-step equations, we did both of these things. We either use the additive inverse or we use the multiplicative inverse, but now we're going to have to do both. And the important thing is that we go additive inverse first, move things around, and then use the multiplicative inverse at the end to make the variable's coefficient 1. So in all of these first 6 problems, we're going to do 2 steps. Move the numbers to one side, so that way the variable term is alone, and then we will make the coefficient of the variable term 1, so that way we have our variable isolated. So let's go ahead and solve each equation down below. Number 1 says 2x plus 5 equals 13. I'm going to start by using the additive inverse to move the 5 to the right side. So I'm going to subtract 5 from both sides of this equation. After doing that, the 5 and the negative 5 cancel each other out, so we're left with 2x equals 8 because we just subtract 5 from that 13. Step 1, just move that 5 to the other side. So whenever I say move, always I'm thinking additive inverse. It was a plus 5, so I did a minus 5 to move it to the other side. Now I have 2x equals 8, so I go ahead and use the multiplicative inverse now. So I'm going to divide by 2, where I could have either multiplied by 1/2 or divided by 2. Those mean the same thing. And in this case, 2x over 2 is just x, and 8 over 2 gives me 4. So my solution is x equals 4. And if we want, we can check by plugging that back in. 2 times 4 is 8, plus 5 does in fact give us 13. Number 2, 7y minus 4 equals 31. We're going to use the additive inverse first. So we're going to add 4 to both sides to move that 4 to the other side of the equation. That leaves us with 7y equals 35, where I'm not going to point this out every time, but notice that when I do negative 4 plus 4, that gives me plus 0, where 0 is the additive identity that we get from doing the additive inverse. But we don't write that plus 0 because it doesn't change anything about our equation. So instead, we essentially are moving the 4 to the other side, where now there's nothing on that left side that has to do with the 4. It's gone. It's on the right side now. All right, then we have 7y equals 35. We're going to do the multiplicative inverse. We can either multiply by 1/7 or divide by 7. Those are the same thing. And it's going to leave us with y equals 5 as our solution. Or again, you can plug that one back in. 7 times 5 is 35, minus 4 gives us that 31 on the other side. All right, number 3, we have z over 3 plus 6 equals 14. I'm going to do the additive inverse first to move the 6 to the other side. So I'm going to subtract 6 from both sides. That leaves me with z over 3 is equal to 8. Notice, by the way, that whenever I'm doing this math, I'm writing the additive inverse directly beneath the number I'm subtracting or adding it from. So the negative 6 I just wrote goes directly underneath the positive 6. I don't just write it randomly on the page, okay? Math works like pancakes, nice clean stacks. All right, we now have z over 3 equals 8. Now you need to remember that when we write z over 3 right here, that really means 1/3 times z, where the 1/3 is in front and the z is in line with that fraction symbol. So we can either think of the multiplicative inverse here as multiply both sides by the reciprocal of 1/3, which would be 3 over 1, or we can think about this as dividing both sides by 1/3. So two different ways I can write this. I can either divide both sides by 1/3 like this, where I don't recommend we divide both sides by 1/3. That is much messier. Okay, instead, whenever we were going to divide by a fraction, that means to multiply by the reciprocal anyway. So let's multiply by 3 over 1, which is really just 3. So I don't need to write the over 1 part. So if we multiply both sides by 3, on the left we just get z, and on the right side we get 24. So z equals 24 is my solution. If we were to plug that back in, 24 divided by 3 is 8. 8 plus 6 is in fact 14. All right, number 4, we have 4x minus 9 equals 15. Additive inverse first. I'm going to add 9 to both sides, which is going to leave me with 4x plus nothing, so I don't write anything, equals 15 plus 9, which is 24. And then multiplicative inverse will make my coefficient of x 1. So this leaves me with x is equal to 6 on the other side. And again, always think about plugging these back in, making sure you're doing them right. Okay, number 5 is our first one that's a little bit tricky. We have 0.2x plus 7 equals 12, otherwise stated as 2/10 x plus 7 equals 12, where we're going to do the same step first, additive inverse, get that 7 to the other side by subtracting 7. So we're now left with 0.2x equals 5. Now we have a couple options though. Okay, so I'm going to show you essentially 3 different ways we can do this. The way I would do this problem is I would turn 0.2 into a fraction where I know that 0.2 is 2/10, and 2/10 is really 1/5. So I would think of 0.2x as 1/5 x, and then the way I cancel out the 1/5 is by multiplying both sides by 5. So after multiplying both sides by 5, I would get that x is equal to 25. Notice that multiplying by 5, what is 0.2 times 5? Well, that's 1. Okay, so multiplying by 5 does in fact make the coefficient 1, whether I had turned 0.2 into a fraction or not. So now, why do I think of it this way? Well, I've tried to convince all of my students of this, but fractions are better than decimals. All right, in most cases in mathematics, we prefer fractions. They actually work out to be nicer most of the time. So thinking of 0.2 as 1/5 allows me to see that the reciprocal of 1/5 is just 5. So nice and easy, multiply by 5 on both sides. An alternative way you could have done this is divide both sides by 0.2. So I'll work this out on the side here. I could have done long division, where I have 5 on the inside and 0.2 on the outside. But if you remember what I taught you guys in our decimal lesson, whenever we divide by decimals, we actually want to use an equivalent fraction. So instead of doing 5 divided by 0.2, okay, where let me write it in 2 steps here, 5 divided by 0.2 is equivalent to 50 over 2. Where notice I multiplied top and bottom by 10 to get to 50 over 2. And then that problem is actually pretty easy to solve. 50 divided by 2 is just 25. And notice that's the same answer I got before. So multiple ways you can think of this so far. We could turn 0.2x equals 5 into 2x equals 50 by multiplying both sides by 10, which is something we're going to see more of later. Or we could turn 0.2x into 1/5 x and then multiply both sides by 5. Or the third way, which is my least favorite way, is pull out a calculator. And if you type in 5 divided by 0.2, you will in fact get that same 25. So now I think that's the worst way because notice I was able to do it very quickly without the calculator. But there are going to be a couple numbers in this lesson, specifically our very last problem, where I'm going to pull out the calculator because the numbers are so big, it would take me more time to do it by hand than to just check with the calculator. So in the website for this course, if you've ever looked at the bottom of the homepage, I have a little note about calculators on there where think of calculators as a tool, just like what we use in gardening at home, like if we're working in our backyards. If you have to cut one piece of grass, you wouldn't get out your lawnmower. You would just go use your hands and rip the piece of grass, or you'd get a pair of scissors. But if you have to mow a whole lawn, yeah, a lawnmower is going to save you a lot of time. It's the better tool. but in general, you need to be the better tool. Okay, if I need to do one very simple thing, I should just let myself do it and not have to go rely on some technology or some tool. So just keep that in mind. Calculators, good, but they have a time and place. And that problem number 5 was not the time or the place. All right, all that said, number 6, we have 3/4 x minus 5 equals 7. I'm going to start with the additive inverse. So I'm going to add 5 to both sides. This leaves me with 3/4 times x is equal to 12. And then now the multiplicative inverse of this, I am going to multiply both sides here by the reciprocal of 3/4, which is 4/3. On the left side, I just get x. And on the right side, we can think of this as 12 times 4 and then divided by 3, which would be 48 divided by 3. So that gives us 16. Or you can think of it as what I consider is the better way here. We can do 12 divided by 3 first, which gives us 4, and then multiply by 4. So 4 times 4 would be that same 16. So I prefer to make the number smaller and then multiply, but either way, you're going to get to the same place. So 16 is going to be our solution, no matter how you got there. Okay, so now those are the truly two-step equations. Not so bad, hopefully. Now we're going to make it a little bit more complicated by bringing in some of our other properties. So many equations, almost all the ones we deal with in general, are going to require some simplification before we can go ahead and apply the steps we just did. So sometimes one or both sides of the equation are going to have to be simplified before we start solving. And the main property we're going to be using for this is the distributive property. So you can see that 2 of the 3 questions down below are going to involve that distributive property because we have parentheses. So we're going to use the distributive property first, and then we are just going to combine like terms on each side before doing what we did in the previous questions to solve. So number 7 is first, we have 3 times the quantity x plus 2 is equal to 18. I'm going to distribute that 3 to the x and to the 2 to get 3x plus 6, and this is now equal to 18. And notice that after doing that distribution, this is exactly like one of the first 6 questions. So all we have to do is do the additive inverse first, so minus 6 on both sides. That leaves me with 3x is equal to 12. Then the multiplicative inverse, I'm going to divide both sides by 3. That makes my coefficient of x 1, and I end up with x is equal to 4. Number 8, we actually don't have to distribute. We just have to combine like terms. We have 5a minus 2a plus 7 is equal to 19. All I'm going to do is combine the 5a and the negative 2a to give me 3a. So I have 3a plus 7 equals 19. This one's nice and easy like the ones up at top. I'm going to do the additive inverse, which is minus 7 on both sides. That leaves me with 3a is equal to 12. And then the multiplicative inverse, I'm going to divide both sides by 3 to end up with a is equal to 4. Hopefully you're noticing that I really like 12s, 4s, and 3s because they show up all throughout my notes. All right, number 9. Just adding one extra layer to this so far. We have 2 multiplied by x minus 4 plus 6 is equal to 10. So I'm going to distribute that 2 to the x minus 4 to give me 2x minus 8. The plus 6 is still there, and same for the equals 10. Now I'm going to combine like terms. So negative 8 plus 6 is going to give me negative 2. So I now have 2x minus 2 equals 10. Additive inverse tells me to add 2 to both sides. This gives us 2x is equal to 12. And then multiplicative inverse, just divide both sides by 2. And we're left with x is equal to 6. So now, I hope you didn't feel as though I was being condescending by calling these ones easy, but the reason I was doing that is because the next page is going to be of the same type, but we're going to make it a little bit harder. And what we're really going to be doing is just including fractions and decimals all throughout the place. Now, this next page is technically unnecessary. You can do everything that's on this page without applying any of the logic that I'm about to teach you. However, by what we're about to do, which is clearing decimals and fractions, it makes the equations easier to solve. So let's go ahead and go through these bullet points, and then I'll explain a little bit more of what I mean here. So at the top here, clearing fractions and decimals. fractions and decimals can make equations harder to work with. We can multiply both sides of the equation to remove those fractions and decimals. So we can multiply the entire equation, both sides of it, using the distributive property to get rid of those decimals and fractions. For fractions specifically, we're going to multiply by the lowest common denominator, the LCD, of all the fractions. Where remember the lowest common denominator, the LCD, is the least common multiple, which is the LCM, of all the denominators. And if you have forgotten how to find least common multiples, remember that was way back at the beginning of our class where we learned about prime factorization. So go ahead and flip back to that video if you need a quick refresher. But I'm going to be taking for granted here that you can find a least common multiple or an LCD because, well, expected skill. So if that one's giving you a struggle, look back at either our fractions lesson, specifically for least common denominators, or back in our prime factorization lesson for LCMs in general. Okay, so now when we multiply both sides of the equation by the lowest common denominator, this quote unquote clears the fractions and gives an equivalent equation that only has whole numbers in it. So for number 10 here, we have 1/2 x plus 3 equals 7. There's only one fraction involved, so the least common denominator is just 2. It's that only denominator we see. Now, before I do what I'm about to do, I want to make it clear that this is a two-step equation, just like the previous page, where you can do exactly the same steps we did on that previous page and get to this answer. You can subtract 3 from both sides to get 1/2 x equals 4, and then multiply both sides by 2 to get x equals 8. There is nothing wrong with doing it that way. This is just something that tends to make it easier on you when there's a lot of fractions. So number 10, I would actually solve like we did on the last page. But then the next two problems, 11 and 12, I would clear the fractions first using the methods I'm about to show you. All right, so that being said, for number 10, the only denominator is 2, so that is automatically my LCD. I'm going to multiply the entire equation by 2. Now, when I do this, I have to distribute the 2 to everything inside, every term. And what a term is, we're going to talk a little bit more detail about when we get to the next question. But for right now, we have 3 terms, 1/2 x, 3, and 7. So I'm going to distribute the 2 to all 3 things. 1/2 x times 2 just gives me 1x. 3 times 2 gives me 6. And 7 times 2 gives me 14. The most common mistake here would be forgetting to multiply the 7 by the 2. Okay, so just make sure that 2 distributes everywhere because it goes to both sides of the equation. Now this equation just has one step left to solve. Additive inverse means to subtract 6 from both sides in this case. And we end up with x is equal to 8, which if you recall from a few seconds ago, I said is the answer you would have gotten doing it the previous page way. All right, but multiplying both sides by 2 right away allowed us to get rid of that fraction, so we don't even have to think about it anymore. Let's see on number 11 how this is going to help us. We have 2/3 multiplied by x plus 4 is equal to 6. I could distribute the 2 over 3 to the x and the 4 and then get multiple fractions in there, where I'd have 2/3 x plus 8 over 3 equals 6. But then I would have to subtract that 8 over 3 from both sides, and I don't really want to do that because then I have to find common denominators to do that subtraction. It becomes more work that way. Instead, if I multiply the entire equation by 3, where I chose the number 3 because the only denominator is 3, so it's automatically the LCD, I can distribute this 3 to every term. So now an important distinction about what a term is. Notice that I only drew lines from the 3 to 2 spots, the 2/3 and the 6. So the entire thing, 2/3 multiplied by x plus 4, this is one term. Okay, because if we were to distribute the 2/3 first, we would have 2/3 x plus 8 over 3, and then we would multiply both of those by 3. Okay, but by distributing the 3 right now to the 2/3, it will then get distributed in the next step to each thing inside. So when we have multiplication of things right here, 2/3 multiplied by x plus 4, this is all one term. And we're going to see that same thing in problem number 12, where it says 1/4 multiplied by x minus 2/3. That is also all one term. So just be careful. The 3 does not get multiplied by the x and the 4. It only gets multiplied by the 2/3 in front, because that is all one term. And when we distribute in the next step, it is as if we did multiply everything by 3. Okay, so the 3 only goes to the front. So now when we actually do this, 3 times 2/3, notice a 3 on bottom and a 3 on top cancel each other to just give us 2. The x plus 4 was unaffected. And then this is going to be equal to 6 times 3 on the other side is 18. Where again, I want to remind you that the most common mistake is forgetting to multiply the 6 by the 3. All right, now it's as if we were in numbers 7, 8, and 9 from the previous slide, where we're going to distribute the 2 on the left side. When we do that, the 2 is going to multiply by the x and the plus 4. So that is going to leave us with 2x plus 8 on the left is equal to 18. And now it's a two-step equation, just like the first couple problems. The additive inverse tells us to subtract 8 from both sides. That leaves us with 2x is equal to 10. Then we're going to use the multiplicative inverse to divide both sides by 2. And that leaves us with x is equal to 5. So at the end of the day, we just end up with a nice clean x equals 5. It was not necessarily easier to do it this way. I could have distributed the 2/3 from the beginning and still got into this x equals 5. But this made it so I don't have to work with a bunch of fractions, which generally myself and students both prefer. All right, number 12. We have 1/3 x plus 5/2 equals 1/4 times x minus 2/3. I need to multiply this entire thing by the least common denominator, which is going to be the least common multiple of 3, 2, and 4. I only need to focus on the fractions that are outside of parentheses right now, because whatever I multiply by is going to get distributed to just those things that are not in parentheses. So even though there's a 2/3 in parentheses, I don't actually care about it right now. If I wanted to worry about that 2/3, I would do it in the next step after I've already gotten rid of these fractions. So the least common multiple, or the least common denominator here, is 12. Okay, the LCM of 3, 2, and 4 is 12. I'm going to distribute this 12 to the 1/3, to the 5/2, and to the 1/4, but notice not into the parentheses because that is all one term over there. Now, 1/3 times 12 is really 12/3, so that just gives me 4x. 5/2 times 12, I can divide by 2 first to get 6, and then times 5 is 30. So this just gives me 30 here. You could have also done 5 times 12 first to get 60 and then divided by 2. But either way, it's going to reduce to 30. 1/4 times 12 is just 12/4, so that's just 3. And then again, that x minus 2/3 was unaffected by this multiplication. All right, now it looks like problem 7, 8, and 9, where I need to distribute the 3 that's in front of the x minus 2/3. When I do that on the right side, I get 3x minus 2, because the 3 on top cancels the 3 on bottom of that fraction. So we're left with 4x plus 30. Now I want to make a note that this 2/3 was just canceled out by this 3. That's actually a coincidence. That will not happen every time that we no longer have a fraction here. If I still had fractions at this step, then it would be like number 10, okay? Where I could just then multiply by the least common denominator again, and it would get rid of whatever fractions are left. So sometimes you have to do this process of multiplying by the LCD more than once. But in this case, once was enough. All right, so now we're going to use the, this is actually the first time that we've had variables on both sides. So we have to move two things around. So we're going to use the additive inverse twice. First, I'm just going to subtract 30 from both sides. Where notice that when I write minus 30 on the right side, I write it under the negative 2. So I'm left with 4x equals 3x minus 32. Very important that I am not subtracting 30 from 3x. I am specifically combining the negative 2 and the 30 to get that negative 32. Okay, so it's very important where you write your numbers down. Write constants under constants and variables under variables. All right, now we do not have the variable term isolated yet, so I have to use the additive inverse again. This time I'm going to use it to move the 3x to the left side. So I'm going to subtract 3x from both sides. That leaves me with 1x is equal to negative 32. And in this case, we don't have to use the multiplicative inverse because we only have 1x over there. If it was 2x equals negative 32, then I would just divide both sides by 2, and then I'd be done. All right, so sometimes we just get lucky and only have an x there. I want to show you guys real quick now. I'm going to actually redo those last two steps just to show you that we could have done it in a different direction and got the same answer. So I'm going to delete from where I subtracted 30 all the way down. And I'm going to do the exact same thing, but just in the different direction to show you that it gives you the same thing. So instead of subtracting 30 from both sides to move the 30 to the right, I can also add 2 to both sides, and that's going to move the 2 to the left. So that would give me 4x plus 32 is equal to 3x, where those 2's cancel each other out. I would then, instead of moving the 3x to the left, I would subtract 4x from both sides to move the 4x to the right side, and that would leave me with 32 equals negative x, because 3 minus 4 gives me a negative 1x there. And I wouldn't be done in this case. I would still have to divide both sides by the inverse, the multiplicative inverse of that negative 1. So I would still have to now divide both sides by a negative 1 to get to my final answer, which would once again be negative 32 equals x. So we get the same answer either way, but it was actually one extra step by doing it this way. And my key to which way you should do it is whichever direction keeps the variable positive, that's the preferred direction. So the first method we did was actually better in my opinion. Even though we get to the same answer, I think the first direction is a little bit easier and more consistent. So the way you tell is just think about 4x minus 3x is positive 1x. So if I move 3x to the left, that'll keep the variable positive. But if I do it the way I just did it, by subtracting 4x from both sides, I end up with negative x left over. So then I have that extra step of dividing by a negative 1. So personal preference, but I try my best to always keep the variable term positive. That way I don't have to divide by a negative at the end. All right, last part of this lesson is how to get rid of decimals. And I want to remind you that decimals are actually just fractions that are being represented in decimal form. And so the way we get rid of decimals is really the same as the way we get rid of fractions. Okay, we're going to be multiplying by a power of 10. Okay, so either 10 to the power 1, which is 10, 10 squared, which is 100, or 10 cubed, which is 1,000, whatever power of 10 we need. And this is going to make all the decimals whole numbers. As an example, 0.2, which is going to be our first decimal, is really 2/10, 2 over 10. So instead of thinking of it as a decimal, if I think of it as a fraction, the way you would clear that denominator of 2 over 10 is by multiplying by 10. And that would get rid of that denominator. Okay, so the reason it's powers of 10 is that every decimal is really just a whole number divided by some power of 10. And that's how we get that decimal form. So now you don't have to think too hard about this. However many decimal places there is, that's the power of 10 we need to multiply by. So if we look at all three problems real quick, the first problem has a 0.2 and a 1.4. That's one decimal place each. So I'm going to multiply by 10 to the power 1. The second problem is the same. 0.5 and 8.5 only have one decimal place each. So I'm going to multiply by 10 to the power 1. But the third one, 2.25, 0.75, and 10.5, the first two numbers have two decimal places. So I'm going to multiply by 10 to the power 2. And you might be thinking, well, the third one only has one decimal place, but it's whatever the biggest number of decimal places is. That's what you're going to use. Okay, so now that being said, let's go ahead and actually do the multiplication. 0.2x plus 1.4 equals 5. Because there's one decimal place in the 0.2 and the 1.4, and that no other numbers have more than one decimal place, I'm going to multiply by 10 to the power 1. 0.2x times 10 is going to give me 2x, where all you do to multiply by a power of 10 is move the decimal place one spot to the side. 1.4 times 10 is going to be 14, and 5 times 10 is going to be 50. Where again, the most common mistake is students forgetting to multiply the 5 by 10. Now it's a nice, easy two-step equation. We're going to go ahead and use the additive inverse to subtract 14 from both sides, which leaves us with 2x is equal to 36. And the multiplicative inverse tells me to divide by 2, so I end up with x is equal to 18. Number 14, we have 0.5 multiplied by x plus 7 equals 8.5. We have one decimal place in both of those numbers, so the most decimal places I see is just 1. So I'm going to multiply by 10 to the power 1 again. Notice when I distribute right now, I only multiply on the left to the 0.5, not inside the parentheses, because that's all one term. So I'm going to multiply 0.5 times 10 to get 5, but this parentheses x plus 7 is staying exactly the same. And on the right side, 8.5 times 10 gives me 85. When I distribute the 5 to the x plus 7, I end up with 5x plus 35, and this is still set equal to 85. And now it's a nice two-step equation. We're going to go ahead and subtract 35 from both sides. That leaves us with 5x is equal to 50. And then we're going to use the multiplicative inverse to divide by 5, which just leaves us with x is equal to 10. All right, one more. Number 15 says 2.25 multiplied by x minus 4 plus 0.75 equals 10.5. The most decimal places I see is 2. There are two numbers that each have 2 decimal places, so the most decimals I see is 2. By the way, if you want to think of it in terms of the way we're supposed to say decimals, it actually gives away what you're going to multiply by. So 2.25 is really 2 and 25 hundredths. Notice hundredths, 100, and 100 is what I'm multiplying by. 0.75 is really 75 hundredths, and 10.5 is really 10 and 5 tenths. So all of my decimal places were hundredths, hundredths, and tenths. The biggest of those is 100, so I'm going to multiply everything by 100. When I distribute, I go to everything except for those parentheses. So I end up with 2.25 times 100 is 225, but that x minus 4 is not going to change. 0.75 times 100 gives me a plus 75 there. And 10.5 times 100, careful, don't forget the extra 0. I have to move the decimal place twice, so this is 1050, where I have to put that extra 0 at the end. Now I'm going to distribute 225 to x minus 4. This gives me 225x minus, and multiplying this one is not too hard if you think of quarters. 200 times 4 is 800, and 25 times 4 is 100. So together, this is going to give me 900. Right, and then I still have a plus 75 and a 1050 on the other side. If I combine like terms on the left, negative 900 plus 75 is negative 825. Where just think of it big minus small. 900 minus 75 is the 825, but because the 900 was negative, I have a negative 825 there. Still 1050 on the other side. And now it's a two-step equation. I'm going to go ahead and add the 825 to both sides. That leaves me with 225x is equal to 1875. And this is the step I referenced earlier where I would use a calculator for this next one. I'm going to divide both sides by 225. Okay. And when I do that, I'm going to get x equals, and I have 1875 over 225. Now, I'm a mathematician who's done this a million times, so I can tell that the GCF is 75 of top and bottom. So I could go ahead and divide 1875 by 75 and divide 225 by 75, and I'm able to pretty quickly get to 25 over 3. I do not expect most people to be able to do that in their heads though, okay? And working that out by hand is actually not that trivial because our divisor is a 3-digit number. So I think that for the vast majority of people, the easiest way to do this is going to be to pull out your calculator, type in 1875 divided by 225. Don't give me that repeating decimal though. Hit the fraction button next to it. 25 over 3 is what I want to see. Okay, so this is one where I would consider this to be mowing a lawn. All right, it is worth it to pull out the calculator to do that one because it's completely non-trivial to see that GCF from the beginning. I probably would have had to divide by multiple things to break it down, break it down, break it down. And by the time I've done all that, you could have just pulled out your calculator and had this done in seconds. So this is one where I think technology is the better way. Personal opinion there, though. By the way, 25 over 3, much better than giving me 8.33 with a decimal or with a line over the threes. We are going to have a lesson about how to convert those repeating decimals into fractions. But luckily for you guys, whenever you get one using Desmos here, you can just click that fraction button and it'll turn it back into a fraction for you. That's all I got for you in this one. Thanks for joining me, and see you in the next one.